Hey guys, what's going on? It's me, Mr. V. Today we're going to be learning about periodic trends and just think about the term trend and how a trend is just, what's trendy, what's the repeating patterns that occur. Obviously like style, there's trends that you see. So what happens every so often? What repeats? So this whole unit periodicity is about how whenever you arrange elements in order of atomic number, you start seeing patterns. Just like that activity you all did last week, where you created your own periodic table, you saw that there were patterns and groupings that repeated regularly. Well, that's what periodicity is all about. So we're going to look at certain properties today, and we're going to see how those properties change or are affected as you go across and down a periodic table. The first property is atomic radius. So, what is the radius? What does that mean? You have to answer. A what? So, what can we find the radius of? A circle, right? So, what is the radius of a circle? Well, what's the diameter? Okay, so the diameter is the full way across, so the radius is halfway across. So, just like in math and geometry, the radius is a measure of the size of a circle, essentially. You're going to see the same thing here. As of now, we've been showing atoms as circles, as particles represented usually as circles. So whenever we talk about atomic radius, we're just talking about the size of the atom, but the textbook will define it as half the distance. Just like in a circle, the radius is half the distance, not like the diameter, which is the entire distance. But this is not from the center of the circle to the outside of the circle. It's half the distance between the nuclei of two identically bonded atoms. Now, we'll break down what this textbook definition means, but simply put, what we mean when you hear the term atomic radius is the size of a circle. The size of an atom, specifically. So on the right, you see the radius of a circle. It shows how big that circle is. It's a measure. We can compare sizes of circles to each other by comparing the radius, or the radii of those circles. Well, we don't know where the outer boundaries of an atom actually are. We don't know where that last ring or that outer circle is. So they look at two identical atoms. So let's say these are two oxygen atoms bonded together, and you measure the entire bond length. If you cut that in half, it's essentially like cutting the diameter in half and getting one radius of one of those circles of one of these atoms. So that's how it's measured, and that's how it's established to simply mean how big that atom is. Now, if you look at the periodic table, these are the trends you're going to see. Now, we know why why it gets bigger when it's going down. At least you should after looking at that activity last week. Everything in row 1 has how many rings? One ring. Everything in row 2 had how many rings? Two rings. So here's one, and then there's that outer one. Everything in row 3 had three rings. So of course, what's going to happen as you go down a family is you're going to increase the energy level. So on the right, why is it larger going down a group or a family? Well, you're increasing in energy levels, which means you're adding more rings. And more rings makes the atom larger. So paraphrase this however you'd like, but simply put, the lower you go down the table, the more energy you have, the more rings that are occupied by the more electrons. So if this is period 2, we see the first ring holds 2 electrons, and it has a second ring holding some electrons as well. Whereas a period 3 atom would have 3 rings. So while on the left you see ring 1 and ring 2, on the right you see ring 1, ring 2, and ring 3. So every time you go down a group, you go down or up an energy level, up in the number of rings. Naturally, it's going to make the atom larger. But let's look at this picture again. It makes sense. As you go down, you're adding rings, the atom's going to get bigger. But what's happening as you go from left to right? They're getting smaller. And this one's a little harder to understand. Why is that happening? So what ends up happening is the number of rings does not change, right? Everything in row 2 has 2 rings. So you're not actually losing rings or making the atom smaller. It has the same number of energy levels, but you are increasing the atomic number every time you go from left to right. The atomic number goes up by 1, which means the number of protons goes up by 1. Now this picture is just showing an illustration. The idea that if the ratio increases, well, the ratio doesn't change, but the number of protons increases, then the number of electrons will increase also. So here in red, this is really what you need to focus on. When you go from left to right, look what's happening to the nucleus. Here, the nucleus is +1. Here, it's +2. As you go on, it's +3. And then finally, +4. And again, this is just an illustration. This is not actually a true row in the periodic table. But you add to the power of the positives. So think of it like a magnet. If you had a positive end of a magnet and its power was 1, that's probably weak compared to a magnet that had the power of 4. Well, the same is true for the negative part of this magnet. Here you have -1 on the outside, -2 on the outside, -3, and -4. So this +4 power on the inside and this -4 energy on the outside, those are going to have a stronger attraction. The positive is stronger, the negative is stronger, so the attraction is going to become greater. And so the electrons move in closer because they're more strongly attracted to these positive protons. So basically think of it as these electrons kind of cuddle in closer to the nucleus because the attraction to the nucleus is stronger. So as you go down the periodic table, they get bigger, but as you go to the right, they get smaller. So on your periodic table, draw the trend lines. For atomic radius, you want to draw an arrow pointing down, explaining how these atoms get bigger as you go down a group. But they get bigger from right to left because of the attraction that the protons have for the electrons. On the right, they're cuddled in very close together, and on the left, they're kind of more spread apart. The attraction is not as great. So across the table for atomic radius, you want to draw an arrow to the left and down. So overall, this is what the trend looks like. It starts here, and it goes to this corner. So this corner up here would be your tiniest atom, and this corner down here would be your largest atom. This is the largest because it has the most rings, and because the electrons aren't as attracted or cuddled in as closely. So one thing you're going to be asked a lot is which atom is bigger or which atom is smaller. And as long as you can follow this trend line, smallest up here, and then down here in the lower left, you have the largest atom, then you can remember how these atoms relate to each other in size. And there it is. So if nitrogen approximately had a diameter, or sorry, radius, atomic radius of 0.75, and arsenic had a radius of 1.33, what do we know about phosphorus and its radius? How does it compare to these two? Well, it's going to be somewhere in the middle, right? It's going to be greater than 0.75, but less than 1.33, because what we know happens is it gets larger as you go down. So what would be a reasonable answer for the size of phosphorus? I don't know, maybe like 1 point something. Less than 1.3. 1.05, anything between these two values, as long as it follows the trend, it makes sense. All right, the next property is electronegativity. You see a few words in here. The first word you see is electron. The next word you see is negative. So what do we know about the electron and its charge? Well, the electron is negative, so this property is all about the electron. It's the measure of the ability of an atom to attract electrons. So what does that mean? Simply put, it's the atom's desire for electrons. Just like people, some people can attract more people to them. Maybe they're friendlier, they're more outgoing, I don't know, better looking, anything. That might attract more people to them. They would have a stronger attraction to these electrons, these atoms. So it's a measure of how attracted these electrons are to these atoms, or how much these atoms desire these additional electrons. Now, what we've seen in the periodic table is everything in group 1, your alkali metals, they have one valence electron. That means one electron on the outer ring. If you recall, how many electrons do all atoms want in their outer ring to fill it up? How many will fill up that ring? 8. So they all want 8. But group 1 doesn't want to gain 7. It wants to give away this one electron. And by giving it away, it has a filled shell just below that outer shell. So group 1 elements have no desire for electrons. In fact, they want to give them away. But a group 17 atom, the halogens, have 7 valence electron. They need 8, like all atoms want. They need 1 right here. So while group 1 wants to give it away, group 7 wants to take it. So group 1 has no desire for electrons. Group 7, they have a very strong desire for electrons. They really want that electron. That way they could fill up their outer shell. And then group 18, the noble gases, do they need any more electrons if they already have 8 in their outer ring? No, they're done. They're filled. So they have no desire for electrons at all. That's why the noble gases, they're kind of the stuck-up ones, kind of off on their own. They don't need anything from anyone. So that's what you're going to see here. When it comes to electronegativity, let's draw the trend lines. The noble gases, you want to circle them and indicate they have 0 desire for electrons. Now what you're going to see on most periodic tables is that's not true. There are some electronegativity values for some of the noble gases, but for the sake of what we're explaining here and in this class, and really for what you need to understand in chemistry, let's just say that they don't want electrons at all. They already have all 8 that they need. Now group 17 really wants electrons the most, so this desire is very high. And group 1 has a very low desire for electrons. As you go down, they have even a lower desire for electrons. As you get farther out in the rings, they kind of don't care about what's happening so far out in those energy levels. So the highest electronegativity value is here. So it starts down here and gets higher up to this point there. And you can see that overall trend illustrated by that arrow. All right, so looking at these values here, again, I want to draw your attention to the top right-hand corner. Now, of course, the noble gases, you see xenon does have an electronegativity value here, and there's exceptions to every rule we give you. But what we're going to say about the noble gases is they have 0 desire for electrons. every atom wants 8 in the outer shell, in the valence shell. And noble gases, group 18, already have those 8 electrons, so they don't need to add any. So they don't want any additional electrons. They have no desire for electrons, so they have electronegativity values of 0. The same is true for the first group, the alkali metals, especially the bottom of the group. These have very little desire for electrons. In fact, they really want to give their electrons away. But think about group 17, the halogens. The halogens have 7 valence electrons. How many do they want total again? They want 8. They just need one more. So if you're just one away from completing what you want, you're probably going to work harder for it than if you were over here in group 1 and we're 7 away. So group 17, because they're so close to their 8, they really want that extra electron, so their electronegativity values are that much higher. Here's an image kind of showing what we're going to talk about next, and that's ionization energies. And ionization energy, if we look at the word, you can see the root word is ion. And this is one of those terms that you need to always remember, but oftentimes most students forget. Does anyone know what an ion is? So it's an atom with something. It's an atom that has a charge. That means it might be a positive ion or it might be a negative ion. A positive atom or a negative atom, those are charged atoms. We call those ions.
Is that like the one with like more protons than electrons?
Yeah, so it's exactly that. It comes down to the number of protons versus electrons. So to make something charged, you have to basically steal an electron or give it an electron. Well, ionization energy is the energy needed to take away an electron. And when we simply define it, it doesn't change much. It's pretty much the same definition. The energy required to remove one electron from a neutral atom. In other words, how much energy is needed to steal an atom's electron? Some atoms don't want to lose their electrons, so they will not let you steal the electrons from them. Again, everything we see about this has to deal with the number 8 and how every atom wants 8 valence electrons. So what group will not let you take a single electron from them? The noble gases. Group 18. Why will group 18 not let you take an electron? They have all 8. They're not going to risk losing one. They're complete. Now group 1, as you know, just like in electronegativity, it has no desire to keep that one. It wants to get rid of it. So you could imagine it's really easy to come over to this atom and take this electron away. Very little energy is needed. In fact, they want to give it away. So it's going to be really easy to steal that electron. And then it's going to rely on the next shell that should be filled underneath. Now, of course, this first ring only fills with 2. Everything else fills with 8. But group 17 and group 18 especially, 18 has all 8 electrons. So it doesn't want to lose a single one of these. So it's very difficult to take from here. So noble gases have a very high ionization energy. Group 17 only needs one more. It would work perfectly if this one came here and they kind of completed each other. Well, group 1 doesn't want it. Group 17 really wants it, and it really wants to hang on to what it has, so it also will have a high ionization energy. It's not going to be really easy to steal an electron from the groups on the right. So that means the noble gases have the highest energy needed. So energy here is really high. That means it takes a lot of energy to steal these electrons. But over here on this end, it doesn't take very much energy. The amount of energy needed is low. And then down here, it's especially even lower. So the reason it's higher to the right of the table on this end is because it's almost filled. It's so close to being filled, it just needs a few more electrons. So it doesn't want to lose any, it wants to gain more. So it's not going to allow you to steal electrons from it very easily. On the left, though, they're very close to having the shell below the outer ring filled. They have 1, 2, or 3 valence electrons. They're not going to gain 7 or 6 or 5. They'd rather just give what they have away, so they want to lose them. And then the ones going down here that show you this overall trend, the reason the ones lower have even a weaker desire for electrons and it's even easier to steal them is because if you think about how many rings this one has down here, this is in period 7. So this atom has 7 rings. It's an awful drawing. But if it has 7 rings and on that outer ring it has 1 electron, the nucleus of the atom, which is positive, has a very weak attraction for this negative because of something called shielding. There's all these electrons in between, right? 8 per ring. And I'm not going to draw that exact, but they kind of shield this outer electron from the positive nucleus. So the attraction is so weak between these two particles that it's real easy to come in and take that electron away. So basically, the more rings you have, it's like the more you have to take care of, the more you have to look out for. And it would be a lot easier for someone to steal from you if you had a lot of land to cover, a lot of area to cover to protect, than if you had very little area to protect. So that's why the lower the group, the lower the energy needed. When it comes to ionic radius, again, we're dealing with the size of an atom. There's no textbook definition here for you, but simply put, it's the size of an ion. And an ion, again, we said was a positively charged atom or a negatively charged atom. Alright, so ionic radius, again, is defined as the size of an ion. And an ion is either a positively charged atom or a negatively charged atom. In this case, this neutral atom lost an electron, so it became this one here. It's a smaller atom. So whenever it loses an electron, think of it like it's losing weight. It's losing mass, and it's going to become smaller. Whenever it loses an electron, it becomes positively charged. Now here what's happening is it gained this electron. So you can think of that as like gaining weight. So this anion, this negative version of the same atom, gained an electron, gained weight, gained mass, gained matter to its outer ring, and as a result, it's going to be even larger. So to sum it up, what we're going to see is a neutral atom kind of falls in the middle. The cation, which is the positive ion, will lose an electron and become smaller as it loses matter or mass, loses the number of rings that are occupied. But the anion, the negative ion, because it gains electrons, you can kind of think of it as like gaining weight. It becomes larger because it's adding more matter or more mass, adding to that outer ring, making the atom itself take up a larger area. So from smallest to largest, the cation's the smallest, the neutral one's medium sized, and the anion's the largest. So again, we go small, medium, and large. And it all has to deal with whether it's gaining or losing electrons, and you can determine that by its charge. Positive means it lost weight, negative means it gained weight, positive means it shrunk, negative means it grew. So that concludes this video and these notes. I guess we're done.